Hello, my name is Bill Thompson. I'm a faculty member at the University of California, Irvine, and this is part 3 of our Lawyer's Guide to Probability and Statistics in Forensic Science. These videos are supported by the Center for Statistics and Applications in Forensic Evidence, or CSAFE, which is in turn supported by NIST, the National Institute of Standards and Technology. These guides are designed to help lawyers understand the statistical statements that forensic scientists make in connection with their testimony, and also to help lawyers understand and evaluate non-statistical statements that don't involve numbers, but that are based, at least in part, on assessment of probability and statistics. Even statements that don't appear to be statistical or numerical often have a basis in probability and statistics that lawyers must understand if they are to evaluate those statements properly. There are 3 videos in this series. Video 1 dealt with the issue of quantification, how forensic scientists estimate the quantity of something. Video 2 dealt with classification, determining how to categorize an item. And in this video, video 3, we'll look at comparison and identification, how forensic scientists answer questions about whether 2 evidentiary samples might have had the same source or a different source. We'll look at the way forensic scientists use probability and statistics when they're asked to determine such matters as whether 2 fingerprints were made by the same finger, or whether 2 biological samples came from the same person, whether 2 tool marks were made by the same tool, 2 writing samples were written by the same writer, 2 recorded voices were the same speaker, whether a shoe print came from a particular shoe, and similar matters. To understand how probabilities and statistics are used in this area, it's important to understand the logic of forensic comparison. That is, how it is that forensic scientists go about comparing items to determine whether they have or whether they might have the same source. In every domain, the logic is essentially the same. The analysis begins by asking what features are present in the samples that are being compared. This is true whether it's DNA samples or fingerprints. The examiner will first try to identify features in each of the items being compared and determine the characteristics that will be used in assessing whether they are, how similar or how different they might be. Once the critical features are identified, the examiner then compares those features, tries to determine whether the items have the same features or different features, and whether there are any important discrepancies between the items. It's at this point that the examiner goes to step 3, where probability becomes relevant. Having observed similarities and differences between the 2 items, the examiner has to ask, how likely are the observed results that I see when comparing these 2 items if they have a common source? For example, if there are major discrepancies between the 2 items that would be unlikely to be observed if they have the same source, then the analysis is easy. If one latent print has a loop pattern and the reference print has a whorl, and the examiner determines that that's just something that would be impossible if they come from the same finger, then the result is easy. The examiner can simply say, I've excluded this item. I've determined that the observed results, that what I observe when comparing the items is sufficiently unlikely if they have the same source that I can determine that they don't have the same source, and that ends the case. But if the discrepancies are not so great that the probability of observing them is that the probability of the observed results are 0 under the hypothesis of the same source, the examiner has to consider, well, how likely is it that I would get that result? And the examiner also has to consider a second question. How likely is it that I would get the results I observed if the items have a different source? But how likely is it that somebody else from the relevant population would have those same features? What's the likelihood I would observe that if it wasn't from the person in question, but was from somebody else? In some disciplines, forensic scientists have empirical data on which they can base such estimates. In DNA analysis, for example, there are databases that examiners rely on when estimating the likelihood of the observed results if the items have a different source. Having observed certain genetic features, certain alleles in an evidentiary sample, the examiner can ask, well, how likely is it that I would observe those alleles if a particular suspect was the source? That's the first question. And then how likely is it I would observe these alleles if the source was not the suspect, but somebody drawn at random from a reference population? And databases showing the frequency of characteristics in reference populations are used in that domain. In other domains, examiners don't have good databases on which to estimate the frequency of the observed characteristics. In that case, they may have to rely simply on their subjective judgment as to how rare or common the shared features are. Their judgment might be educated based on some research, but they may lack a specific empirical basis for the estimate and have to just make an educated guess. At that point, the analysis may stop, as I'll explain in a bit. Some forensic scientists simply stop at step 3 and report their estimates of the likelihood of the observed results under the different hypotheses regarding source. But it's common, particularly in the United States, for forensic scientists to go on and take a 4th step, where they make a decision to report a particular conclusion based upon their estimates of likelihoods. So, for example, if they conclude that the likelihood of the observed results is very high if the items have the same source and extremely low if the items have a different source, then they may simply decide to report that the items have the same source. So the possible conclusions that forensic scientists report after that analysis vary. In the United States, it's common for them to make categorical statements. They might simply say it's a match, or say that they have identified the item as being the source of the mark in question. Sometimes they make statements about the probability that the items have the same source. So an examiner might put a number on it, saying there's a 99% chance these items have the same source, for example. More commonly, rather than putting a number on it, they'll simply state in a qualitative or non-numerical way something about the probability of the same source, saying something like it's very likely that these items have the same source. This is a set of reporting categories recommended by SWGDoc, which is an advisory body for document examiners, for how document examiners should report their conclusions on comparing handwriting samples to determine if they were written by the same person. And what SWGDoc recommends, and this is typical of many forensic science fields, is a range of options. If the examiner thinks that the observed results are very likely if from the same source and extremely unlikely with a different source, they can report an identification. Say, I'm convinced. It passes my threshold of decision, and I will report that they have the same source. Or they could say there's a strong probability, highly probable they have the same source, or somewhat probable, or there are indications. If they're not sure, they can say it's inconclusive, indeterminate, or they can go the other way. They could say indications that they did not have the same source, or probably did not have the same source, or strongly probable not to have the same source, and the strongest conclusion is elimination or exclusion, could not have had the same source. Okay. The important thing to realize about this kind of categorical reporting is that it requires examiners to set a threshold for reporting each category. The examiners are basing these conclusions on an assessment of probability. How likely is it that they would observe what they observe in the comparisons if the items had the same source or a different source? And they have to decide whether the relative probability of the observed results are high enough with the same source relative to different source to justify reporting something like identification or strong probability. This requires the examiners to set a threshold. The threshold, there's in most disciplines, there's not any specified numerical value or probability that constitutes the threshold. Each examiner makes a decision subjectively about whether their threshold has been reached, which raises questions. This is a rather subjective process there's a subjective threshold built in many cases upon a subjective evaluation of probability. So there's a lot of subjectivity here that raises questions. Psychologists, for example, have commented that when experts make judgments based upon subjective evaluations and subjective criterion, there often is a potential for contextual bias. That is, for the experts to be influenced improperly by other information about the case, by the context. And there has been research into this, and evidence of contextual bias has been found in decision making in a number of forensic science disciplines. There are studies, and I can provide the full references to these, but there are studies showing contextual bias in document examination, fingerprint interpretation, crime scene analysis, bite mark analysis, even DNA interpretation, blood spatter analysis, forensic anthropology, and so on. And what the studies typically do is ask examiners to make the same comparison while providing different background information. It's been observed, for example, that latent print examiners are less likely to call to latent prints a match, or to say that to reach a conclusion of identification, if there's other evidence suggesting that the suspect in question might have a strong alibi. That's just one example of the kind of contextual information that might influence the way decisions are made. An important point to realize is that these biases can occur quite unconsciously. Examiners typically are not aware that they're being influenced by contextual information. The influence can occur entirely unconsciously, and so a perfectly conscientious analyst trying to be as objective as possible can be subject to contextual bias without even knowing it, and that could be a problem. Another problem with these categorical reporting categories is that they require a certain leap of logic that can be problematic. The examiner has to go from the observation that the items share unusual or rare characteristics to the conclusion that the items have, or probably have, a common source. How does one make that logical leap? You could ask, for example, how rare do the shared characteristics need to be to justify concluding that the items definitely have a common source? That's the answer to that is not obvious, and if you ask forensic scientists this question, often they are not able to tell you the answer. I think logically the answer is that the shared characteristics have to be rare enough that they're unlikely to occur more than once in the entire population of items being questioned. All right, so in thinking about whether the items are rare enough, the examiner has to think about rarity and the risk of duplication. Now, sometimes this is done formally with a set standard. The FBI has set a standard for reporting an identification of two items as having the same DNA profile and being from the same person. So the question is, when you compare two items and find that they have the same DNA profile, how rare does that profile have to be before the examiner can simply report that they are from the same person? The FBI has set a threshold for that, saying that if the frequency of the shared profile is less than 1 in approximately 250 billion, then the examiner can report that the items have the same source. Well, what's the logic of this? Well, the thinking of the FBI is that if you're talking about a population, say, of the United States with 300 million, if the frequency of the shared profile is less than 1 in 250 billion, it would be unlikely that any of the 300 million people, other than the one in question, would have it. This threshold is simply an arbitrary one, but at least they state in advance what it is. Now, let's consider how rare would the characteristics of a latent print have to be before one could logically conclude that they'd be unlikely to be duplicated in the human population. Well, I mean, I've heard latent print examiners say that they can identify fingerprint as coming from one finger to the exclusion of all other fingers on Earth. But if there are, say, 7 billion people in the population of the Earth, and if each one has 10 fingers, that's 70 billion fingers. And so presumably what the examiner is saying is that they can determine that the characteristics observed in two prints that they're comparing occur at a frequency well under 1 in 70 billion. And they can do this without an empirical database, just based upon an educated guess or subjective judgment. Now, understandably, there is some skepticism about such claims among the academic community, although many practitioners continue to make those claims. So we've talked about the logic of identification. How about the logic of saying that the items probably have the same source? So how rare do the shared characteristics need to be to justify the conclusion that two items probably come from the same source? Well, the answer to this question is it depends. For those of you who've looked at the video on categorization, it's quite similar to asking how low does the false positive rate of a classification procedure have to be before we can be convinced that an item classified in a particular category belongs in that category. And what we showed there is it depends on the a priori likelihood the item belongs in that category. It depends on what other evidence there is that the item belongs in that category. And the same thing is true with regard to forensic comparison. How rare does the shared characteristic have to be to say that two items have a common source? It all depends. To illustrate this, let's talk about a DNA case. Let's assume that a criminal perpetrator commits a crime and leaves DNA at the scene. And let's assume that police have developed a suspect and taken a DNA sample from him. The DNA samples are compared and found to have the same DNA profile. How rare does that profile have to be before we can say this is probably the perpetrator, that we've probably got the right person? Well, to make it more explicit, let's assume that the expert says the random match probability, that is the frequency of this characteristic in some reference population, is 1 in 10 million. If the frequency of the matching characteristics are that low, can we say that the suspect is probably the source? Prosecutors tend to think so. Prosecutors sometimes say, well, if the match probability is 1 in 10 million, that means there's one chance in 10 million that the defendant is innocent. Is that true? It turns out there's a problem with this statement, and this is what is sometimes called the prosecutor's fallacy. It does not logically follow that a match on a characteristic found in one person in 10 million means there's one chance in 10 million that the matching person is not the source. That does not logically follow, as any smart defense lawyer can explain. What will the defense lawyer say in response to the prosecutor? Well, a smart defense lawyer will say, well, wait a minute. The suspect, or our defendant, he's not the only person who matches. If there are 300 million people in the United States and the profile occurs in 1 in every 10 million, we would expect there to be about 30 people who would match. Okay, so if you looked across the country, you would find, you wouldn't know where they were, but you would expect there would be about 30 people. All right, and so that hardly, if there are that many people, can we say that that there's only one chance in a million, or one chance in 10 million, that it didn't come from one particular individual who we know matches? Some defense lawyers carry this a little far and say, well, we would expect there to be 30 matching profiles in the United States, and so the probability that our suspect who matches is guilty is only 1 in 30. Now, this is also a fallacy. This doesn't logically follow either, for reasons that a smart prosecutor can explain. Here's the logic. The prosecutor is going to respond, it's not necessarily true that there's one chance in 30 that the defendant is the source of the DNA found at the crime scene. Out of the 30 people who would have matching profiles in the United States, how many really could have committed this crime? If it were the case that all 30 of the people who have matching profiles were identical to our suspect in terms of their motive and opportunity and other evidence, in terms of their a priori likelihood of committing this crime, if they were all the same, then yes, okay, it would be 1 in 30. But it's very unlikely that all 30 of the people are as likely to have committed this crime a priori as our suspect. The 30 people who have the matching profiles could be anybody. It could be, a policeman from Peoria, a military officer, a minister from Duluth. There could be a wide range of different people, some of whom couldn't possibly have committed this crime. And so we certainly can't assume that the probability that the suspect committed this crime is only 1 in 30. Might be higher, might be lower, depending on what how likely the other people were to have committed the crime. And so we don't know. The defense lawyer likes this answer. What this analysis shows is that it actually is impossible to tell the probability 2 items have the same source based solely on the rarity of the matching features. You also have to consider something about the a priori likelihood that they would match about the other evidence. But then that raises an important question about the logic of forensic inference. If it's impossible to tell the probability that 2 items have the same source based solely on the rarity of the matching features, then how do forensic scientists make this leap to go from the items have shared features, which is what the forensic scientists observe, to the conclusion that they probably have a common source? How do they make that leap? The only logical way for them to make that leap is for them to make assumptions or to draw conclusions about the strength of the other evidence. In order to say that the defendant is probably the source, they have to also assume or conclude that the defendant is a likely suspect a priori, that there's other evidence that suggests that he could have done it, or that doesn't rule him out. And that raises an important question for lawyers, which is, should forensic scientists be doing that? We have a situation where the conclusion being expressed by the forensic scientists now only depends partly on the analysis of shared or unusual features in the items compared. It also depends in part on the forensic scientists' assumptions or conclusions about other evidence in the case. Now we know that forensic scientists are sometimes influenced by evidence beyond their domain of expertise, and we know this because they sometimes tell us. Here's testimony that I thought was quite interesting from a transcript of a forensic odontologist who did a bite mark comparison and was cross-examined about the underlying logical basis for that conclusion. What did the expert rely on in concluding that the bite mark in question could have been made by the defendant? And the expert testified that he relied partly on similarity between the characteristics of the bruise or bite mark and the characteristics of the defendant's dentition, but was also influenced by other information, particularly once it was found that DNA evidence linked this particular defendant to the crime scene. And the bite mark examiner says, well, you know, if I find that the DNA evidence matches 2, that increases my confidence that he made the bite, that he was the biter, and so I might upgrade my confidence level. I might, rather than saying I could not exclude him as the source, I might say that he probably is the source. So the examiner is saying he's relying partly on DNA evidence to reach a conclusion about the strength of the bite mark evidence. Is this a proper thing for a forensic scientist to do? It's not just odontologists. I've heard forensic scientists in other domains talk about considering the a priori likelihood that a defendant is the source in deciding how to report their conclusions. And often they justify this by talking about how rare a feature must be to be duplicated, and saying, well, you have to consider the size of the suspect population or the number of potential contributors. If you're a latent print examiner, for example, and you are trying to decide whether a particular latent print came from the defendant rather than some other individual in the entire human population, then, as noted before, you'd have to be convinced that the shared features of the fingerprint are extraordinarily rare to assure that they would not be duplicated in the entire human population of 7 billion people and 70 billion fingers. But what if the reference population is not the entire human population, but just people who you think had access to the crime scene? And maybe you think only a small number of people could have committed the crime, and that this defendant is one of them. Then, rather than asking, would the characteristics that I see in the 2 prints be shared by someone else in the entire human population, you'd say, well, would these characteristics likely be duplicated in a small number of people? Maybe there are only 5 or 6 people you think who could have committed the crime, and you don't know who they are, and you haven't looked at their prints, but what's the likelihood that one of only a small group of people would have the rare characteristics that I see in these prints? In that case, the characteristics don't have to be nearly so rare as if you're distinguishing the suspect or the defendant from the entire human population. And so if you can assume there's a small number of potential perpetrators, then you can reach the conclusion of identification, or reach the conclusion that the prints are likely to be from the same source with fewer shared features. Again, I ask, though, should examiners consider this fact? If they do so, should they at least disclose that they've done so? And the problem here is that it requires the forensic scientist, the forensics examiner, to look beyond their area of expertise. A latent print examiner who's doing what I just described is not just considering the features of the prints when reaching conclusions. That examiner also has to consider the strength of other evidence that indicates that the defendant in question was likely a priori or unlikely a priori to have been the source of the print, and how many other people could have been the source of the print. And so, and all of these are matters that are likely to be contested at trial. And so an examiner who takes this kind of thing into account is having to take positions or make assumptions on a contested issue at trial that has nothing to do with their area of expertise. Is this something an expert should do? Well, concerns about the logical basis for categorical conclusions have led some forensic scientists to conclude that they should not go to step 4 in our logical steps. So we talked about the logical steps: analysis, comparison, assessing probabilities, and optionally making a decision about reporting same source or different source or likely same source. What if the forensic scientist just stopped at step 3? It would preclude all this question about what's the logical basis for making a decision. And that's why a number of experts in forensic science think examiners should not report identifications and should not report source probabilities at all, but should limit themselves to talking about their estimates of the probability of the observed features if the items have the same or different source. What you see here is some language from the European Network of Forensic Science Institutes, issued in 2015, recommending that their members and that their member practitioners in Europe confine themselves to reporting conclusions by either expressing the value of a likelihood ratio, that is, by giving the ratio of the probability of the observed results under alternative hypotheses, or by using a verbal scale related to the value of a likelihood ratio. What would that look like? Well, for a likelihood ratio, a shoe print expert on seeing a certain amount of similarity and might say the evidence is 100 times more likely if the print was made by the suspect's shoe than a random shoe. That would be a likelihood ratio. Or they might apply a verbal label to the likelihood ratio and say something like, this provides moderately strong support for the proposition that the suspect's shoe made the print. So the verbal labels usually talk about the degree to which a likelihood ratio of given size supports one hypothesis as to source over the other hypothesis. DNA experts in the United States often testify something like the following. The observed results are 10 million times more probable if the contributors are the defendant and the victim than if the contributors are the victim and a random Caucasian. That is a likelihood ratio. Now, the important thing to notice here is that this does not require the examiner to make any decisions about whether the results are strong enough to support identification or whether it's likely or not likely that any particular person is the source. This is a statement about the strength of the evidence for distinguishing the hypotheses, not about the probability that the hypotheses are true. As far as verbal equivalence, a number of organizations have recommended language that could be used to explain likelihood ratios to a jury or a trier of fact. This set of labels from the Association of Forensic Science Providers, a UK-based organization, suggests the following verbal expressions based on the size of the likelihood ratio. If the likelihood ratio is over 1 million, as it might be in a DNA case, the expert can say that provides extremely strong support for the hypothesis of common source of the two items being compared. If it were between 10,000 and 1 million, very strong support. If it were 100 to 1,000, moderately strong support. All right, how do we know these labels are the correct labels? These are simply an effort by a professional association to recommend language that they think will communicate the intended meaning adequately. Whether these are the proper labels is an issue that I think warrants additional research. Research by psychologists on this issue is currently underway. The idea that experts could make statements about the likelihoods rather than statements about their conclusions on whether the items have the source or not is gaining some support even among the traditional pattern matching disciplines. There was some interesting language recommended by the Defense Forensic Science Center, which is the U.S. Army lab, and originally drafted by Henry Swafford, who works at the lab. That lab has decided not to report identifications anymore in latent print cases. Instead, where they find an association between two prints, they will note that the prints show a high level of correspondence, and then they'll make this statement. The likelihood of observing this amount of correspondence when two impressions are made by different sources is considered extremely low. So this is kind of a qualitative, non-quantified statement about the the probability of the observed results if the items have a different source. And it says it's considered extremely low. I personally don't like the passive voice here. It makes me wonder, considered low by whom? And how do they know? Nevertheless, it's an interesting example of how a forensic scientist can report a conclusion about a comparison without making a decision to report it as an identification or not an identification, simply by stopping at step 3 and then stating something about the conclusions at step 3 regarding the likelihood of the observed findings if the items have the same source or a different source. The advantage of reporting estimated likelihoods over reporting identifications or source probabilities is that there's no need for any arbitrary and subjective decision threshold. Experts don't have to ask, how low do my estimates have to be before I will say it's an identification or that it's very likely to be the same source. If they're simply reporting their estimate of the probability, they don't need to make the decision as to whether a threshold has been passed. No need to apply a threshold at all. And that may reduce one area in which subjective judgment can play a role. It may also reduce overclaiming, right? May possibly reduce the potential for contextual bias. It certainly eliminates the need for examiners to think about the a priori likelihood that this particular suspect could be the source, right? They simply report the likelihood of seeing what they see, observing what they've observed if the suspect is the source or is not the source. They don't have to think about whether other evidence indicates he's likely or unlikely to be the source. There are concerns about reporting likelihood ratios. Whether lay people will understand them correctly and give the intended meaning is an issue that needs additional research. Some concerns about whether lay people can understand what likelihood ratios are and what they mean. There's also been a lot of skepticism expressed about experts reporting numbers that are based upon subjective estimates. Michael Reisinger, the prominent evidence scholar, called these numbers from nowhere, which is, I think, questioning their provenance. I've actually heard worse terms used for them. I heard one statistician refer to these as rectal numbers in reference to their assumed source. So there's questioning as to whether there's a proper basis for such numbers. This questioning is also seen in the recent report from the President's Council of Advisors on Science and Technology. Their report said specifically that the frequency with which patterns would be observed in different samples, presumably if there's a different source, is an essential element for drawing conclusions. And it's not a matter of judgment, it's an empirical matter to which only empirical evidence is relevant. Okay, so this is a rejection of any kind of numbers based upon subjective judgment. However, you need to understand that this problem also affects other reporting methods. If you're concerned about the subjectivity of the likelihood estimates, the problem isn't solved by not reporting those estimates, but simply reporting a decision based on those estimates. If forensic scientists report their likelihood estimates, at least we know what those estimates are. Whereas if they're saying it's an identification, or it's probably the source, it's not so clear what their likelihood estimates might have been that led to those conclusions. To illustrate this, let's imagine two different experts. Expert number one, Mr. Explicit, follows the approach recommended by the European Network of Forensic Science Institutes. Compares two items, estimates the likelihood of the observed features of the items have the same source, estimates the likelihood of the observed features of the items have a different source, and then reports those estimates and their ratio. That would be the European approach. Another expert, Mr. Implicit, an American, follows the standard American approach, Does the same thing at step 1 and 2, makes these estimates, but provides no information on what his estimates were, and simply reports a decision as to whether those estimates pass the threshold to reach a certain conclusion. If relying on subjective estimates is a problem, isn't it as big a problem for Mr. Implicit as Mr. Explicit? I don't know the answer to that question, but I'm asking. The PCAST report says that if forensic scientists are relying on subjective methods where the estimates of likelihoods cannot be verified or don't have an empirical basis, they should subject themselves to black box studies to determine how accurate their subjective judgments are. So in other words, if latent print examiners, for example, they can't say exactly how rare the features they've identified in 2 prints are, but we can make them participate in a study in which they are required to look at pairs of prints that we know to be from the same source or from a different source, and then we can test the accuracy of their classifications. This brings us back to the this basically converts the comparison and identification problem into a classification problem and asks about the accuracy of the classification. So PCAST suggests that studies of this type be done. These are called black box studies, and that examiners, when reporting, when they report an identification, say, they have to also report what is their true positive and false positive rate in order to give the trier of fact some idea of how accurate this kind of testimony might be. Seems like a reasonable approach. I largely agree with the assessment of the PCAST report, and I think they're making excellent points. But I would like to add a few caveats or elaborations on the PCAST report. The first thing to understand is that the false positive and false negative rates, which they are suggesting that experts report, are going to depend on the expert's threshold of decision. You know, how rare does it have to be before the expert will report common source, for example? And that threshold of decision is likely to vary depending on context. And what that means is that the threshold of decision that's applied while examiners are participating in a black box study may not be the same threshold of decision that's applied when they're doing routine casework. And so these black box studies could underestimate or overestimate the rate of true and false positives. The black box studies that have been done so far, for example, tend to show extremely low rates of false positives, which could be because analysts are applying, knowing they're being tested, are applying a very high threshold. They're not reporting an identification unless they're really, really certain. But they show much higher rates of false negatives where they fail to exclude items that are from different sources. Whether they'd apply the same threshold in routine casework, we don't know. There's been some proposals that the black box testing be done or incorporated into routine casework, and I think that's an excellent idea. It's also important to understand that the false positive and false negative rates developed in black box studies are going to depend on the difficulty of comparisons. The false positive and false negative rate that occur in a particular black box study will probably depend a lot on how difficult the comparisons would be. And this is another reason why the results of black box studies may not correspond exactly to the probability of error in a particular case. There's so much variation according to the difficulty of comparison that there's unlikely to be a single error rate for any procedure. It makes no sense to ask what is the error rate for latent print analysis, for example, because the error rate for latent print analysis probably varies a lot depending on how difficult the comparison is in a given case. We may be able to learn the relative risk of error when making different kinds of comparisons under realistic conditions, but there's probably no single number or set of numbers that would characterize the rate of error for any particular procedure. It's likely to be a range. Finally, the PCAST report assumes that examiners are going to be reporting match no match or or identification, non-identification, and that's the preferred reporting format. And as already discussed, maybe that's not the best way for them to report their results. I think an argument can be made that they're better off reporting something closer to a likelihood ratio or some statement about the strength of the evidence for distinguishing hypotheses rather than a conclusion about which hypothesis is or is likely to be true. Another issue I'd like to comment on is the concept of a relevant reference population. When forensic scientists are estimating the probability of the observed results, if two items in comparison have a different source, they often ask themselves, well, how often would these observed results occur in a reference population? If in a DNA case where the perpetrator is thought to be an African American and the suspect is an African American, DNA analysts often will use a database of African American samples when estimating the probability of the observed results if the items came from an African American other than the suspect. All right, so the characteristics of the case often determine what database is relevant. In deciding that issue, forensic scientists need to think about what the pool of alternative sources is. If in the DNA case, it was known that the perpetrator was an African American, and so only African Americans were likely to become suspects, then the pool of alternative sources is other African Americans. On the other hand, in a case where it wasn't known what the race of the perpetrator was, then the pool of alternative sources should include all different races and ethnicities that make a difference. The question has to be who other than the suspect might have been the source, and forensic scientists, in order to know what the relevant reference population is, may need at least some contextual information about that. They don't need to know how likely any particular person would be to be the source, but they need to know something about the general characteristics. Similarly, if firearm examiners were comparing a bullet to a gun, if the bullet is .22 caliber and they're asking what kind of gun might be the source, if not the gun in question, obviously they have to consider other .22 caliber firearms that could have fired the bullet. Right. Questions will often come up about whether the database used adequately reflects the characteristics of the pool of alternative sources. So to illustrate, let's imagine a case where we know that the perpetrator of a crime is a male with a deep voice and a heavy Boston accent. Does that make a difference in what database we use? Well, the answer is it depends. If we were talking about a DNA case, and the question is, does it make a difference that the suspect has a heavy Boston accent? The answer is it probably doesn't make any difference because there's no evidence that the genetic characteristics in human populations vary based on accent. So the database or databases that would ordinarily be used for DNA testing would probably be just fine. You wouldn't have to make some special adjustment because the perpetrator had a Boston accent. But the result could be very different if instead of doing DNA analysis, we were doing automated voice comparison, where it may well be that the probability that the probability of the observed results for a recording of the perpetrator would be quite different in a database of people who speak with a Boston accent and a deep voice than it would be in the population in general. And so in that instance, it may well be the case that the general database would not be adequate. This is an analysis that has to be done in every case. Forensic scientists and lawyers will need to think very carefully in some cases about whether the database used adequately reflects the characteristics of the pool of potential alternative sources. Finally, now we're nearing the end of the tape. Let's do a quiz to see how well you've understood what you've seen so far. Let's imagine a case where DNA was deposited last week at a crime scene, and that it's determined that the DNA profile of the crime scene DNA sample matches that of Elvis Presley. And the lab determines that the random match probability, that is the frequency of this profile in the human population, is 1 in 1 million. Only one person in 1 million would have this profile, but Elvis has it. What is the probability that it came from someone other than Elvis? Now, is it 1 in 1 million that it came from anyone other than Elvis? Or would you say it cannot be determined based on the facts given? It depends, among other things, on whether Elvis is alive. Or would you say the probability it came from someone other than Elvis is 100% because Elvis is dead? If you've been paying attention, you should rule out option A. That is the prosecutor's fallacy. It's fallacious to go from the frequency of the matching characteristic to conclusion about the probability of the source. Right? I think it might be fair to say there's a 100% chance it's someone other than Elvis because you think Elvis is dead. But notice what's happening here is that your conclusion about the probability it came from someone other than Elvis is not depending at all on the DNA statistics. It's depending on whether you think Elvis might be dead or not. That's what determines whether answer B or C is correct. I actually think the correct answer is B, because you can never be entirely certain that the king is dead. That brings us to the end of this videotape series. Those who have been with me from the beginning, I hope you came to me with a skull full of mush, you lawyers, and that you're emerging thinking like statisticians. Anyone who has comments, suggestions, criticisms, corrections, I'm easy to find, and I'd be very happy to hear people's reactions to these videos, particularly suggestions for making them better and more useful for the legal community.